Kia ora, Year 12. In this video, I'm going to go over the idea of using differentiation to find a rate of change in a word problem. And this goes with the Walker section, pages 33 to 38, and I've done worked solutions to those questions, and they're up on Google Classroom. So I think the easiest way to get into this is just to start with some problems. I've got 6 old exam questions that I'm going to go through. The first 3 fit exactly with these Walker pages here. And then the last 3 link up with finding maxima. Okay, so you probably want to have watched that video before you look at this one. The biggest change that we're going to see here is that until now we've been working usually with x and y as my variables. So we might have y is equal to that, or we might have, I don't know, y equals, I'll do another parabola, y equals x squared plus 6x plus 9. Right, so we know for this one here that this would be a graph that looked like this, and then we can find dy by dx, right? And we've talked about that over and over as being the gradient function, and that shows me that if I take my ruler and figure out the slope of the tangent to the line at any point, that number is going to be dy by dx. So the slight change in how we think about this now is we're always going to be thinking about the derivative as a rate of change. So let's just start by looking at some problems and seeing how they're different and how they're the same. So this is an old exam question. You can see straight away there's no x and y, right? We've got a tank that is being filled up with milk, and the 2 variables are the depth of the milk, d, centimetres, at a time t minutes after pouring started. Okay, so it works exactly like it did before. We could rewrite this as y equals 1/4 x squared plus x. And now that should look really familiar. But we're never going to bother doing that, right? We just get used to working with whatever variables we've got. And so we're asked to find the rate at which the depth of the milk is changing 5 minutes after the pouring started. So the first thing we're going to do is we're going to differentiate. And that gives me the rate of change for any value of t. So d dash of t will equal, well, so it's going to be 1/4 times, bring down the 2, and then it's t to the power of 1 plus 1. Right, now most of you will be going, why is she doing that so slowly? Well, that's just in case any of you have forgotten how we differentiate when we've got a fraction sitting here, right? So cleaning that up, that gives me my derivative, d dash of t, and d dash of t is equal to 1/2 t plus 1. Right, but the question here is asking us find the rate at which the depth is changing 5 minutes after the pouring started. So what we have to do here is when t equals 5, we have to evaluate the rate of change. So d dash at 5 seconds is equal to 1/2 of 5 plus 1, which gives me 3.5. Now, the units for this are going to be centimetres per minute, right? Okay, so that's the first one done. Now here we started with d of t, so the notation that I used was d dash of t. We could also have written that as d by dt, just like we usually write dy by dx. Okay, so that's that first one done. And that was a question from back in 2013, and that was an achieved question. The second one is similar, but we're looking for something different. Okay, so just jumping back to the first slide, we're starting to get the idea of what these 3 situations are. The first one that we just did was the easiest. It's when we're given a value of the independent variable, right? So in that one there, we were told work out the rate of change when t equals 5. And the other 2 are where we're given, we're told to work out when the rate of change will be something, or when the depth or the height will be something. So let's figure out which one is example 2. Okay, we've got a stone being dropped into a pool, and that makes circular ripples on the surface of the water. And the area of those ripples is given by the formula for the area of a circle, a equals pi r squared. So here we can differentiate and we can get dA by dr and that will equal 2 pi r. Remember, pi is just a constant, so don't let it freak you out. It just sits in there, right? And here we're asked to find the rate of change of the area of the ripple with respect to the radius. So what that means is we started with our area formula, and we're saying when r changes by a little bit, what happens to the area? And we find that by differentiating. But this time, we're trying to find the rate of change when the area is 49 pi. So we're not told what value to substitute in here. We have to go back to here and work it out. So we've got the area is 49 pi, but we know that the area comes from the formula pi r squared. So we have to solve this equation to figure out the value of r. So we're going to get 49 is equal to r squared, r is equal to 7, and now we take that value and we find the rate of change, so we substitute it in. So when r is equal to 7, dA by dr is equal to 2 times pi times 7, which is 14 pi. And it's, what units is that? Well, the area is measured in meters squared. So it's meters squared per meter. The other way I could write that is I could just chuck that in my calculator and say that that's approximately 43.99 meters squared per meter. Don't get too stressed out about the units for these at level 2. You'll get the hang of it as we go along. The easiest way to think about it is to look at the rate of change and know that if the top one is area, then the first unit will be the area unit, so meters squared. And then here we've got dr on the bottom of the fraction, so we've got meters on the bottom of the unit. Okay, so that's a merit question, right? Because the skills involved here are a little bit more. Going over it one more time, what did we have to do? Well, we started out by differentiating to figure out the rate of change for any r value. But then we weren't told the r value to use. We were told what was the rate of change when the area was 49 pi. So we had to solve to find r equals 7 and then substitute it back in. Let's look at another example. Okay, I think this is from the same exam, and this is also a merit question. So the distance around a tree is given by g meters, g for girth, and that's t years after it's planted. So we have to figure out when will the rate of growth be this much. So g dash of t is equal to negative 0.01 t plus 0.15, and we have to figure out when this will equal 0.04. So we're solving this equation to get a value of t. So we get negative 0.01 t is equal to negative 0.11. Dividing through gives us this. So the rate of growth will be that much after 11 years, right? So after 11 years, growth rate will be 0.04 meters per year. Okay, so that's those 3 examples are the ones that are done in the Walker book, and you can see that they match up to the 3 that I've written here. But I want in this video to keep on going with something slightly harder, which is the link up to maximising things. So 3 more exam questions, and these are all merit questions, but they all start quite similarly to what we've just done. So in this one, a diver dives into a pool, and this is the depth that she reaches 2 seconds after she hits the water. And so you'd expect we're going to come out with negative numbers in here, and we do. So we have to find the greatest depth that she reaches. Now, what it doesn't say here is using calculus, but it says that for the whole paper. So I know that some of you will be going, well, we can do this using our graphing knowledge, right? So we know that we've got a parabola. Let's see what factors we've got. We've got t here, and then we've got 1.25 t minus 4. So we're going to have an upside down parabola. It's going to look like this. We could do this using symmetry, but we're not going to do it that way. Instead, we're going to say the greatest depth that she reaches is going to be where the gradient is 0. So the first step here is to differentiate. So d dash of t is equal to 2.5t minus 4, and that has to equal 0 for a maximum. So 2.5t equals 4. T is equal to 4 divided by 2.5, which is 8/5, which is 1.6, I think. Yep, 1.6 seconds. So that's not my answer, but that's telling me that the maximum depth will be at that time, right? So we take that t value, and now we substitute it back into here to figure out the depth. So d at 1.6 is equal to 1.25 times 1.6 squared minus 4 times 1.6. And that gives us negative 3.2. Now that makes sense because we are talking about, what have we got? We've got a swimming pool. Oh, so that picture I did up there was completely wrong. I was thinking we were thinking about a ball being thrown in the air. We're talking about someone diving, so it goes like that. It's an up the right way parabola. Sorry about that. Okay, so this is saying that the time, the depth is 3.2 meters, right? So the time when the greatest depth occurs is 1.6. So the greatest depth is 3.2 meters. Right, one more example. We've got a skyrocket being projected into the air. So in this case, we do have an upside down parabola. What is the maximum height that the skyrocket will reach? And again, we're going to do it using calculus. So we're looking for when will the gradient be 0. So h dash of t is 39.2 minus 9.8t. That has to equal 0 for a max. 39.2 is equal to 9.8t. That gives us t is equal to 4. I think it's seconds. Is it seconds? It must be. Yep, seconds. So what's the maximum height that the skyrocket will reach? So we take that and now we substitute it into the value of the function. So h of 4 is equal to 39.2 times 4 minus 4.9 times 16, giving us 78.4 meters. Right, one last one for you to do. I'm going to run out of time with this one, but I'll just, I'm going to give you the answer for this, and you can have a go at this and maybe show me in class. So will the firework break the 50-meter limit? I have got time to finish it. H dash of t is equal to 20 minus 10t equals 0 for a maximum. So t must equal 2. We take that to figure out the height at 2 seconds, and we get h of 2 is equal to 40 minus 5 fours is 20. That gives us the maximum height of 20 meters, and that's less than 50 meters, so it won't break the limit. So there you go. Quite a lot in this video, guys. So I think you will probably benefit from pausing it and then trying to do each question on your own and making sure that you've got all of the little steps. And make sure to do all of the questions in the Walker book on this as well. Thanks for watching.